So carbon stars have more carbon uh, in their atmospheres than they do oxygen, which gives them a ruby red appearance because of the production of carbon monoxide. A carbon star is one where the carbon and oxygen are inverted. So you have oxygen right here, you have carbon right here, but there's more oxygen than there is carbon in the solar atmosphere. This is solar elemental, this is in the sun. The red is hydrogen, the yellow is helium, and other is expanded out. You see there, these are all the other main elements in the solar atmosphere. And of course, all the other elements are way down here. Things like, what's that? Calcium, sodium, nickel, all that stuff. Notice how they actually have molecules in there. Yes, there are molecules in the solar atmosphere, because that's what happens when a star evolves. It takes those elements and it forms molecules, more and more complex molecules. This paper right here, Carbon Stars, I have written, in astronomy, carbon stars are stars which have more carbon than oxygen in their atmospheres. This is measured in spectroscopic surveys. It is also inadequate for 21st century astrophysics. It is more fitting to remove the designation of carbon star as being some specific type of star, and to understand that carbon increases in abundance as the star evolves, as measured against helium. Now, I choose helium for a couple of reasons. One reason is that it's a noble gas. Hi, Celeste. And it doesn't react. It doesn't form molecules with itself or with other elements. It's unreactive. First reason. Second reason, it's very light, which means as the star evolves and it loses its lightest elements, lots of that helium can be lost very easily. And third, helium is abundant in natural gas deposits on Earth as well. It is extremely abundant in young hot stars like the sun. So to correct the astronomers, this is in the paper here, instead of taking their spectroscopic surveys in which most stars are hydrogen and helium when they're very young, which they are, and then saying, well, it's a carbon star, and then saying, oh, well, there's more carbon there than oxygen, it's inverted, and then labeling the star as a carbon star. That's not good science. That sort of muddies the water. If they were to say it's a carbon star, they should be like, well, it's mostly carbon, which makes more sense, because most young hot stars are helium and hydrogen. It should be called helium and hydrogen stars. But they don't. They call them carbon stars because the spectroscopic surveys, the appearance of the star makes them really red, like a ruby red color. But that just shows that they put too much importance on the star spectrum, especially when the star doesn't keep its spectrum as it evolves. It ceases shining as it moves down the transformation curve it should be on. So a carbon star would be up here, but eventually it'll stop shining, and then you won't be able to see that carbon from its own heat and light, and it'll sort of lose its capacity for astronomers to observe. Yeah, they'll have more carbon than oxygen, and they'll keep more carbon than oxygen as they evolve. But again, calling it a carbon star, it does astrophysics and astronomy a huge disservice. And it places importance on spectroscopic surveys only as being the ultimate in determining what happens to a star as it evolves. For those new listeners here, we know that stars cool, collapse, and die and become life-hosting worlds called planets. So eventually, astronomy is going to realize that a planet is a highly evolved star, that the same objects, or a planet can shine when it's really, really hot and bright, or we can call, planets or stars, it doesn't matter. They're the same objects. Keeping on track with this carbon star talk, the reason why I wanted to measure carbon against helium, and I mentioned that earlier, is that helium on the Earth is in very, very, very low abundance. It doesn't even technically make a chemical composition of the crust of the Earth, because it escaped earlier during the Earth's evolution because it's so light, and it's unreactive, which means it didn't combine to form molecules or chemical compounds in large quantities, as did the other elements. So what this does is give us a good estimate for how old a star probably is. So given young hot stars have a lot of helium versus their carbon, which is right here, the helium, they have a lot of helium per their carbon, which is of course expanded out, so it's a lot less than that. But this will be highly inverted, and we know it's inverted because Earth, the majority of carbon on the Earth, is in the form of life and limestone and marble. The chemical composition of marble and limestone is you have a carbon in the center, you have a double bond with oxygen, a single with oxygen, a single with oxygen, and you have your calcium ion +2, so negative, negative, +2. And that's what calcium carbonate looks like. You know, the stuff that composes seashells. Seashells are all over the place. That's what they are. That's what the mollusks form to protect themselves when they're growing. Yeah, there's that, and basically it just shows that the amount of heavier material will increase in its mass percentage as the star evolves. So inside of a star, the hydrogen, in order for that to stay together, because it's super, super light, it would have to combine with the oxygen, which makes it a heavier water molecule. And that's how a lot of the helium and hydrogen and oxygen stay put. As well, oxygen is very reactive. So towards the later stages of the star's evolution, when the interior mantle is forming and the crust is forming, that oxygen that's in huge quantities in young stars stays also in huge quantities on the very evolved stars like Earth. That's why the crust is mostly oxygen and silicon. Those two elements are very reactive, and they stay around for a long period of time. But in short, it's best to move away from astronomers' standpoint that the stellar evolutionary history can be determined by a star spectrum, which is completely untrue. The spectrum is only present in the star when it's very, very young. And as it cools and collapses in itself, it loses its heat, it loses its light, it stops shining, and it becomes what astronomers call a brown dwarf, or a hot Jupiter, or what have you, a gas giant. And that gas giant or hot Jupiter or brown dwarf continues cooling and collapsing and becomes an ocean world, which then further cools and collapses and then forms a differentiated rocky ball in its center. So the very process of planet formation isn't a process that you can actually observe. I mean, you can look at objects that are in different stages, but you can't look inside the object to see the planet forming in its interior. I mean, maybe you can with inertial measurements, but you know, that's going to take a lot of time, and taking inertial measurements of exoplanets is going to be almost impossible because they're so far away. That being said, it's better to take carbon as opposed to helium, because when the star evolves, it's the helium that's lost in the most quantities versus taking carbon versus oxygen, because the oxygen sticks around. It'd be better to measure it against something that's actually lost, so you can get an actual a much larger ratio to determine how old the star is. So, for instance, Jupiter is around 700 million years old. It would have a lot more carbon as opposed to helium than the sun does. The sun has a hell of a lot more helium than carbon. And then it continues on further down the line. Eventually, that thick Jupiter atmosphere will be lost, and all the helium that Jupiter had will be lost as well, because it's unreactive and it's very light. And the carbon will begin building up and, you know, forming those organic molecules and compounds, and eventually life down the road. But I just wanted to share this paper with you guys. I'll link it to the bottom. it's a very different worldview that we're dealing with here. It's very, very different, very new, and it takes a lot of creativity and open-mindedness to fully understand it. And I'm sure a lot of people that watch these videos already have that. That's why they're here. All right, guys. Later.